Yeah, so I haven't graded the homeworks this week yet, but I haven't really looked at them. But this next week is on the seawater greenhouse thing. So there's like a video that tells you dew point, wet bulb temperature, dry bulb temperature, relative humidity thing. It's psychometric chart. Anyway, so you can just watch that video. It pretty much tells you how to do it. There's some questions of using that, like given a certain thing, how much water could you evaporate, that type of thing. So if it's too bad for you, let me know. But basically, it shouldn't be. I think that video pretty much explains it. And then this other one, let's see. So evaporating seawater, though, you need to, let's see. So evaporating regular water is one thing, and condensing regular, like just pure waters, kind of with the psychometric chart. But then it's got salt in it. You need to use like a thermal function to account for the osmotic pressure of the salt in the water, shifts the vapor pressure. If you can't find that, let me know. It's just like some equation to put in the salt content, and you can get the vapor pressure of the water, and then you can figure out from the vapor pressure how much would evaporate or whatever it was. And then I don't know, there's a bunch of, like there's a wiki page on the seawater greenhouse, and there's a bunch of papers they publish. So I put a few of them in there to look at. One is to use seawater greenhouse on, like you have an osmosis plant, reverse osmosis plant, and then it ends up with brine, and then you take the brine and you can get more water out of it to use a seawater greenhouse with brine. That's like 2018. And this Oman thing was written by some Omani guys, which somehow they must have been working with Charlie Patton, right? But they don't cite him in the paper, but it's the same kind of thing. Like it's basically the seawater greenhouse thing, 2012. So they've been doing it for a while. The first paper is like 2005 or something, I think. So it's a while ago. This Davies was was working with Patton. So he's at a university. He's at Birmingham now, but he was at some other university, Warwick, I guess, before that. So in the UK. Anyway, so hopefully that's okay. Anyway, so I wanted to just, all right, so then yeah, there's 2 tours we can do. The water company wants to do the tour. So we can do that on a Thursday after class. No, in November.
Around the 16th.
Well, we can pick the day. I sent the email he sent. There's a bunch of days. So you can pick whatever day anybody wants. Well, only one person has said they want to go to the waterworks thing. So we need maybe 5 would be good. Anybody can go. He doesn't have to be in the class. And then it's pretty interesting. Like I think it's kind of interesting, but it's going to take, it's probably like 20 minutes from here, and then it's going to take at least like an hour and a half. So say we get there at 3:30, or we'll be there till like 5:30. But it's pretty interesting, like science fiction place, because these big indoor halls with sand filters, like as far as you can see, I mean, it's really science fiction. Then you go to the carbon filtration. So they put all the city's water through carbon filtration, which is like black pools. So you see this kind of weird looking black water thing. And then they have their own regeneration of activated carbon. So they have a big tower in the furnace where they bake the carbon, get rid of the gunk in it. And then they treat all the water with UV. That's just like a big pipe with a UV thing on it. It's kind of interesting. The building itself is from like the 1920s or something. Parts of it are really old, so it's almost like a museum in a sense, you know. It's like it's kind of a weird place. Like it's worth going to see. Anyway, they're happy to show it, you know. There are chemical engineers that work there. And then the other thing is that I thought it'd be fun. I went to this recycle place at Rumpke, you know, a while ago, last year, I guess, just because I was doing a project on that stuff. So I thought it'd be good to see and talk to the people there. But anyway, it's pretty worth going to. It's like not far. That's like 5 minutes by car from here. It's on Vine Street. But the guy is like, oh, can you do it Monday or whatever, or the 30th, whenever that is. What I sent the date, right? And it was on a Monday at 9 a.m. So I don't know. Yeah, so we can't do it then. All right. So I gotta tell him, I guess I'll tell him what time. So basically we need either Thursday after class or Friday. That's what I'm looking at. All right. So, all right. It's definitely worth doing, but if we can't do it, it's all right. Um, I mean, recycling is a big problem all over the world here too, but so it's pretty interesting what they're doing there. They have robots that pick the garbage. Like, and then they also have like a bunch of different things. They have like, they can identify like PET, like these bottles with IR. So they have a computer and it sees like, oh, there's a PET bottle and it puffs air and the thing hops over a little fence. So they collect all the PET stuff with a robot, not a robot, but like a computerized sorting machine. And I don't know, they get the cardboard out of so whatever you put in the recycle bin. So they have cardboard's lighter, so they blow air and the cardboard like flies into the air and it catches in another bin. It's pretty cool to see. It's right. They're running through like tons of the stuff, you know, huge amounts. They have bulldozers feeding it, right? So it's a huge operation. And all the Cincinnati waste goes into that one site and it's all being like sorted there. They have a big one in Columbus too. I think the one in Columbus is larger than here. But anyway, or it's growing or something or other. So, but this is pretty cool to see, I think. And it's like right next to UC. It's not far from here. So anyway, it'd be good to go there. And I'll just tell him we can only do it on like a Thursday afternoon or Friday. It's all day Friday, or he likes to do stuff in the morning. That's the problem. So maybe Friday morning would be the one that we would go for. It'd probably be like 9 a.m. Friday morning. He's like an early morning person. So I mean, I think everyone wants to tour that place. It's almost like I think they're kind of lined up with people waiting to tour it. So if we can do that, I think it'd be pretty cool to see. And then the 80 acres is sometime after that in November. It's sometime in November we can go out there. I'm thinking of getting I don't know, usually I get a guy from University of Colorado that was graduated here with an undergrad in chemie and then went to grad school and now he's a professor out there. But I don't know if it's kind of worth it because he did some stuff with photocatalysis type stuff for making hydrogen gas. But he's not really doing that now. He's doing other things. So, and then it's interesting to hear him talk from his background, but then it's kind of like, not sure it's really worth it. It would be on Zoom. And then I could get like Mao Bing 2 does this biodiesel stuff. You'd have him come in and talk if you guys want. I don't know if that's of interest, you know. He's pretty dynamic. And then Ming Lu's doing chemical environmental. I think they're both, is Mao Bing chemical or he's like chemical environmental. I think they're both environmental chemical. But she's doing biochar. She could talk too. So I don't know. I'm debating whether it's worth having them come in, but if you guys want to hear them, I can do them. Like if there's popular demand, I'll do it. You know, I also like, I think last year or the year before, I got a guy that's doing like wind turbines, right? I can't find anybody that can talk about wind turbines. But there's a guy that invented this new way to make power from wind where you ionize the air and then the ions fly through the ions deposit to the ground and you end up with a charge differential. And that so you can use wind power just by doing this ionization thing. He's kind of an inventor in Albuquerque, so it'd be on Zoom too. But we could have him talk. And there's a group in the Netherlands that's doing kind of the same thing. They take water, they make a water mist, charge it, and the water mist flies out, and then that leads to a charge differential. They both are getting energy from wind, not using propellers, you know, not using a turbine or anything. So he'd probably be happy to talk. That seemed to go like not that great though, because he's really just like a physicist, and he didn't seem to understand that it's kind of interesting, like what he's doing, you know. And then I think they ran out of money too, so like, you know, it's a little bit of a funny thing. So I'm a little hesitant to bring him back in. Maybe I'll find some other people too. If you guys have anything, any of those things sound interesting, let me know. Like email me if you think that sounds interesting, and I'll get those people. And then if you can go on those tours, let me know. Kind of let me know right away, or as soon as you can. Like, so once we get to 5 people, I'll just say we'll do it. You know. Anyway, so I wanted to just, so this thing goes through, the notes kind of go through like different solar things, you know, like stuff you can do with solar. First, the simplest things like a greenhouse, and then you can heat water with solar. So you can like make your own. Basically, you can just get a box, paint it black, put water tubes in it, and then run water through it, and it heats it up. So you can heat water. It's a pretty easy thing to do. So there's a lot of these like do-it-yourself water heaters that people have made that you can see on the internet, basically. But there's a book called something like Renewable Energy for the Evil Genius or something or other that tells you how to make a water heater from an old radiator, like kind of solar water heater. These are kind of like more commercial solar water heaters. Basically, it feeding through, and this is feeding through these evacuated tubes like Patrick Sherwin was talking about. So you have a tube, it's painted black in the middle, it's got vacuum, totally insulated, then the water runs through it. That's one option. Another option is that you can, well, you can put that kind of tube, you can get a parabolic reflector, put the tube at the focus point, and then you can run a heat exchange fluid through it, like oil, right? So, and then this can get pretty hot, and then you can use that to do a lot of things, like run a steam generator, or you could kind of do a lot of things with the hot oil, you know. And once you can get this kind of parabolic track, this would track the sun. So it's a heliostat, and it also has this like evacuated tube, and then it's got a heat transfer fluid. This kind of setup, right? So anyway, that just kind of shows what that evacuated tube, like a cross section, I guess, of it. But then there's these kind of focus solar collectors. So this is really right. So this Euro dish has what's called a Stirling engine up here. So it makes electricity from a heat engine. And you can do it with this parabolic reflector that has a heliostat that tracks the sun. So it can rotate in a circle and it can tilt, right? So it can go anywhere the sun goes. And then you can also do it with a Fresnel lens. So these kind of parabolic reflectors are more expensive than a Fresnel lens. This is like a sheet of plastic. And then if that piece came out and this piece came out, it would make a lens, right? So you just get rid of the mass of the lens, just have these like steps in it. It does the same optical, because all the action of a lens is where the air meets the material. So the index of refraction change makes it bend the light. Right, so it doesn't matter, the mass of the lens doesn't make any difference. So you can make this into just a printed sheet, like an injection molded PMMA sheet. can act like a gigantic lens if it has the right step shape to it. So that's called a Fresnel lens. See, that's used pretty often. So this thing with the Stirling engine, it doesn't want me to do it, but this should be easy to find. Oops. This is the problem. Let's get back. Here. And it's pretty hard to deal with. Anyways, at the bottom of this, it shows basically if you have a hot, so you have the sunlight somehow focused in with a parabolic on a piston, and that's attached to some kind of a generator or an alternator. And then there's a cold part that's hidden from the sun that has a radiator on it. Basically, the heat expands, and then if you have a kind of a flywheel situation here, it'll push it back down, and the cold will contract. And that's basically a Stirling engine. It's like the simplest kind of heat engine. All you need, and you can use low level heat with this. So just basically, there's different designs for it. You can do it that way. You can do it with one single cylinder with two pistons in it. There's like 3 or 4 designs for it. Anyway, Stirling engine is like the answer to people. They say, what do you do with waste heat? This is one in action. It's kind of interesting to look at, I guess. Taylor Swift. I think everything is Taylor Swift. This link definitely works. That's my thing. That's not helpful. What is this? Here we go. Gonna go to the thing I want or not? We will find out. Thing isn't that exciting, but is that it? That's all it did? It's definitely, this works on my computer, you know. My computer, I can just go like here and just click this and it will go to it. And if I read this, this is the link, right? Copy that. Click yes will enable the hyperlinks in this file. Can't open. There's a bunch of links I want to go to, so it's worth trying to figure this out. Let's see. See, this won't even let me go.
If you have a utility meter like this on the side of your house.
All right, so I'm not sure that it's worth it to figure out how. Anyway, so they have a Stirling engine here that's working off they have all this is right. So all this stuff, it's just pipes, like a painted black box with pipes in it, tubes, right? They're also painted black with a piece of plastic over it. Then the heat from that thing goes over here and heats up the hot part of a Stirling engine that's pumping water. So it pumps water when the sun's out. That's it. So you can see the thing's kind of moving. And if they zoom in, yeah, they zoom in on the, so the Stirling engine is like a slow kind of dinosaur kind of motor thing that's moving, right? But it can do work. And the amount of heat is like, it's not boiling water that's going into this. So it's basically, they're using it to just feed the cows or someplace, right? So anyway, so it's possible to do that. It's probably a way to fix this stupid problem, right? All right, so that's Stirling engine. Anyway, so this is a setup where it makes electricity. You have a parabolic mirror, focuses down on the Stirling engine here. It's basically concentrators are useful if you're trying to do this kind of thing. The ultimate concentrator is going to be like heliostat. So you have a field, like a field full of mirrors that track the sun, focus the sun up on a tank at the top that's painted black, and then it's filled with the system of liquid salt. So you melt the salt with the sunlight. So this gets to like 2,500 degrees at the top, and then the salt goes down, and at the bottom there's going to be like a tanks that store the molten salt that are insulated, right? Then you run like water through those tanks and it boils, makes high pressure steam. That runs into a steam generator. And you just make electricity with that. So basically, it's basically a coal plant after the thing there, right? So these are pretty large. This is a Spanish. This is at Sandia in New Mexico. You know, kind of showing as a prototype or something, I guess. That's one of these in Spain, and there's one in Nevada. I didn't put a picture of that in here, but so there's a few. There's one in Morocco. Let's see. Oh no, I wanted maps. I think go to Morocco. Morocco solar farms. That's pretty good. Satellite picture. So yeah, these are solar panels. So next to it, they have a solar panel set up. And then they also have a heliostat here somewhere. So it turns out, like, here's the heliostat, right? This is in Morocco, in Africa, right? So the problem is, like, these aren't as, this is just a bunch of mirrors that focus light onto this tower, and at the top of the tower is this glowing molten salt. The molten salt goes into the tanks, and then attached to that is a steam plant. Like over here, this is a steam plant. I'm not sure what the fans are here. It's like fans, but anyway. So these are just mirrors. It's just a huge bunch of mirrors that point the light to the top of this thing to like make electric generation. Turns out like solar panels are cheaper and work better. There's a lot less moving parts. So if you look at all the rest of these, it's going to be, these are the newer ones, are just solar panels. Like they gave up on the heliostat thing. This is near Western Sahara where that wall is. Like if you look in here, Western Sahara is like down here. If you look in there, there's a wall. The longest wall in the world is here. Morocco built it to separate Algeria from Western Sahara. And they kicked all the people out of Western Sahara. It's because they have phosphate in Western Sahara. That's it isn't gold or something they're going after. It's phosphate for fertilizer. So the Moroccans, they actually took 200,000 people and marched them across the border to occupy Western Sahara, and drove the Western Saharis out basically into Algeria. You know, then once they were out there, they constructed this wall that goes along basically the entire border of Western Sahara to keep them from coming back in. There's not a huge population there, you know, basically things happen. These are the Canary Islands. That's like a vacation place. There's also one of these in Nevada. See if I can find that. Yes, solar farm is like the thing that's going to work here. Oh, I thought, what's the name of that place? Crescent Dunes. So that's like, you can see it here. You can actually see the thing glowing, I think, in this. They haven't changed it. So it's the same kind of setup. Yeah, this one's glowing. See, it's the lights on it and it's like just totally saturates the whole thing. And there's a salt tank, so there's a coal plant there. So this isn't far from Las Vegas. I think the power from that goes to Las Vegas. And these things, I think this is, anyway, this is like where they did the testing for the hydrogen bomb is out here too. Wherever Las Vegas is. Arizona. Las Vegas must be where all this stuff is. The testing for atom bombs. You can see the craters here if you look right. Wait, somewhere up here is the Nevada test site. It's a huge area and it's just all craters. Anyway, so those are these solar concentrators. Again, like they haven't, a lot of these technologies they tried it out. So they first tried this in Spain. And then also Spain also is the first one to do, since Ethiopia, they have some of these, this company Aroa Solar has put in some of these solar concentrator fields, small scale, then with a diesel generator backup. And they've put in a few of those around, mostly it's hard to tell if that's really, working. This is another technology. So this is a technology also in Spain, right? So you built a huge chimney out of plastic. It's not a brick chimney, and then you tether it with ropes, and then you have a field that you throw rocks in and you paint the rocks black. Then you just put polyethylene sheet over the top of it. And then the air, like the rocks heat up, the air rushes in, and it goes up this tall smokestack and it runs a giant turbine in the middle of the smokestack and you make electricity with it. Right, so they're building one of these in Australia. There's one that existed in Spain, but because this chimney's made out of plastic, a big storm came and it fell over. The whole thing is like isn't really, it looks impressive, but it isn't much to it. It's basically this entire thing is made out of plastic and rocks. And in one turbine, that kind of generates electricity. So it's kind of an interesting idea. The point of this is that in order to make this thing economical, you need a really tall smokestack to get a good draw out of it. It has to be super tall. If you try to do this on a small scale, like in a village in Africa, I mean, it basically doesn't work. Like you don't get enough wind to make the turbine move. This is in Botswana, where they've tested this out. The idea and it's a complete failure. It's like because the smokestack isn't tall enough and the collection field isn't large enough. I mean, you can do a calculation of this and figure out how tall a smokestack you actually need to get a draw to drive the turbine. But this doesn't cut it. You need something kind of like this, where these are houses down here. So it's a huge area. There's no mirror here. It's just black rocks with polyethylene sheet over it. I mean, they found out that the underneath that, because it's shaded, like the humidity level of the air changes, and also it's got good sunlight coming in. So basically they get a lot of growth of plants under this thing. So it becomes like a giant greenhouse. So there's also could be an added benefit, or there's also maybe you have to put something in to kill the plants that grow in it. Anyway, so that's another one of these kind of ideas, large scale ideas.
Like make that cement and then just paint over it. If they do that in a abandoned parking lot and then just paint it all black.
Yeah, you could do it in a parking lot and just if you put a roof on it. Yeah, you'd have to put a plastic roof, like polyethylene sheet over it. And then in the middle of the parking lot, put a huge chimney made out of plastic. Yeah, you could do that. I mean, it drives a turbine. I mean, this Spain one was a prototype, and then this is supposed to be a commercial unit in Australia. I'm not sure what the status of that is. Enviro Mission. Let's see how it's doing. Actually, I didn't check that. It's called Enviro Mission. Australia, that is a thing. So I'm not sure what their progress is. I mean, anyway, it still says developer. It doesn't say producer. So Melbourne based, blah, blah, blah. they're trying to get money apparently, right? This is the prototype picture, concept, animations. I don't see that they're actually have done this. I think this is still a twinkle in their eye kind of thing here. But it's been done in Spain, and it was attempted to be done on a small scale in Africa, and it was a failure. So I'm not sure how the parking lot idea might be a good idea, but the area here is pretty large. I mean, it's hard to see how large that area really is, but it's huge. I mean, this is a road, right? So you can see it's a pretty big area. It would have to be a pretty large parking lot. And then you'd have to have this giant tower. Then you need to have ropes that hold the tower up, tethers, you know. So the tower thing has to be kind of engineered. Anyway, yeah, hot water. So there's a bunch of different kind of, so the hot water system. So this is similar to that parabolic mirror thing that the Go Sun is using, right? In fact, they use the same tube in here, evacuated tube to cook in, and they have this same kind of weird parabolic shape thing to get the light to come onto the tube. So that's a standard. They didn't invent that kind of reflector thing. It's just a standard. So yeah, you can do like with this kind of solar water heater, you can have it circulate. So you can have a heat transfer fluid in it if you want. And then you can have it as a backup to your house water system. People use these for pools, you know, so it's going to be like a pool heating system. This shows like a pool, and then the solar heater to keep the pool water warm. Right, just the system where you could run that through it. You can kind of engineer the flow of these things. Similar idea. Then there's just business of just using sunlight to dry things, right? There was some stuff, there was like a study in Ethiopia. There was a homework I had in the past looking at this, comparing different ways to dry skins, you know, skin tanning operations. But they need to use heat, and then can you use a solar heater to do that? So that's kind of the stuff I have on water heaters. It's not really, I mean, it's pretty simple, right? And then passive solar is even simpler. Like, so that I had a guy come through that actually talked to the class about Iranian. He was from Iran, and they have this thing where they from prehistoric times, like the Persian Empire. So they would get the water because it's an arid country. So they get water from the mountains, and they have underground tunnels to carry the water to into the desert, you know, and the people are living in the desert. So they all call them qanats. And these are like, they don't even know really the origin of these things, but they were man-made and during the Persian Empire, I think, pretty much, you know. And they run through the cities. So they don't have air conditioning there. So they have this kind of, and it's a dry atmosphere. So you have this kind of evaporative cooling. Like the wind, the hot air blows over the qanat and up through the house, makes it humidified. And then at the top of the houses is these wind towers that pull the air. And there's a prevailing wind across the desert. So you just kind of design this thing that way. Looks something like that. Right? It's kind of like a way to do design air conditioning architecturally, like without having. And then like in Africa, so people have looked at this in the West, like kind of like where you put walls to get the air to flow through houses, like you design better to get this kind of flow. But in Africa, like they've been doing that for a long time. Like if you look at how they basically have these high roof, it's always pretty warm. So everything's open. There's no windows. And then you just have these high roofs to collect the hot air. So the place is cool even in the summer, you know. So it's basically designed similar to this kind of idea, but it's just like the architecture that they naturally have is like that. Then there's this idea, this Thrambe wall idea. So you have like you build like a black wall, put plastic sheet over it. If you cut the holes right, so you can move the black wall up and down. So if it heats up, then it makes the hot air rise into the room. So you can heat a house this way with just a wall, a black wall that just lets the air flow through. right? I mean, you can move this thing up and down depending on if it's winter or summer. That's the idea. Like you can use it to cool in the summer and to heat in the winter. It'll pull air out. In the summer, it's pulling air out. In the winter, it's pulling air in. I think that's the idea. So it pulls air in, heats up against the wall. There's some, this is a Michigan fishing shack where they use it to heat. And the guy claims that it gets to like 80 degrees in the middle of the winter. It's on top of a lake. And then there's this is like a horse ranch, I forget where it is, in Montana or something. And basically this is what they did. They took the wall, the horse ranch, it's like a, whatever you call it, like a track where they run the horses around, and painted it black on the outside, put this framework up, and then put plastic sheet over it. And it's just a gigantic Thrombey wall, and that's all they use to heat the thing in the winter in Montana, right? So it's possible to do these kind of simple architectural things to just use solar, like without any kind of weird thing. This is in Peru. They're using a Thrombey wall to heat their house on top of a mountain somewhere. Right? People are happy to get the free heat. There's ways to use a Thrombey wall and then store the heat in rocks. You know, so a lot of times they'll use like a rock kind of sump or something where you can run the air through it and just heat up the rocks and then use that as a battery for the heat. Then there's this business. So there's just been like the ACS Chemical Engineering News. They just had an article about this. I put a link to this on the webpage, but it's like how you actually, that one I could get pretty easily. I can figure out how to do this. Just put it. Put that up. So it's like an article from Convention News about how just like painting the roof white can like cut the heat, you know, in a place like, somebody has come up with this idea of using this bisphenol. So bisphenol is like, actually the water bottle is made of bisphenol A. So it's like bisphenol A has this carboxylic group and an aromatic and another carboxylic over here. So it can, if you put in a dialcohol, it condenses and makes PET. It's a polyester, right? So anyway, so if you put that bisphenol into this kind of complex molecule in hot weather, it hydrolyzes and condenses in cold weather. So it makes it white. It changes color. So you can paint the roof with this stuff, and then supposedly it will like cool and heat in the right time of year, right? So this cooling and heating is a pretty big deal if you live in with climate change, you know. So like in India, this is a BBC thing about these people, like New Delhi. So 150 degrees C is like normal there now. I mean, so they're getting 120 degrees, so hot, right? So basically, just by painting the roof white like this, I think they can change the temperature inside the apartment by something like 20 degrees, 10 or 20 degrees, like cool it down. Because it's just, the sun's out, it just absorbs on the roof. If you can reflect it, like that's a huge difference. So the idea is just like paint everything white. And this organization, I forget what organization it is, but they're funding, it's kind of a women-based organization, and they're funding the women to paint roofs. So they show them just painting the roofs, and they show like how the quality of life improves. It's a pretty simple, like partial solution to this problem. This is more complicated, like chemical. You can also just, and this is aluminous, adding different reflective, like aluminous reflective paint, right? So basically there's different kind of pigments you can use to enhance the reflection of light. Trees have this weird thing. I tried to look this up because I did some proposal on this a while ago, but basically inside a leaf, there's kind of a, so like there's a problem with, if you're in the military and you do like an IR scan to see where people are, then you find where like it lights up and you shoot a cruise missile at it or something, right? So a $50,000 cruise missile, after some little guy, so it's kind of a waste of money, but anyway, so anyway, plants though don't show IR, like they're invisible. They don't reflect IR. So it'd be like if you look at IR at a tree, it's just like not glowing at all, even if no matter how hot it is. And they think it's because like the cells of these cube, like a cell and a leaf is a cube shaped thing, and the light gets like trapped in that cube. So kind of somehow the light comes down and traps in it, so it doesn't lead to this like reflection thing. Anyway, so it seems like I was looking for something on that because it seems to have something to do with this roof thing, like we could paint it with anyway, if you go into the woods, it's a lot cooler, right? And the trees aren't really hot. Like if you touch the leaves, they aren't hot. So that's the idea, like basically because of the shape of the cells of the leaves within the leaves that they somehow trap the light in it or something or other. Anyway, so the military is like looking at how they could make cubical pigments to paint tanks with, or whatever you want to paint, so that it doesn't show up in IR. So it could do the same thing that biomimicry, to mimic how the leaves work. But so far, I haven't gotten any money for doing that. Sounds like a good idea, but anyway. So that's like some of the simplest things. This is something, if you go to like New Mexico, like Albuquerque, I lived in Albuquerque for a while, and then like California, so it's dry, right? So you need a certain relative humidity in order to use this thing. But basically this is called a swamp cooler, and it's just a drum, and at the bottom it's got like water bath kind of, and it runs through a water bath, and then the air flows through it and evaporates the water. So it's dry out, so it's good. It humidifies the air, and when the water evaporates, it cools it too, significantly. So it's like 100 degrees outside, it ends up being like 70, easily. So all you're doing is just blowing air. There's just a fan. There's no condenser or anything in this, right? So that's called a swamp cooler, but it only works in certain places. Like you need to have the right kind of atmospheric conditions. In other words, dry. It has to be dry. Which brings you to the psychometric chart, right? So anyway, so this is a plot of dry bulb temperature. So that's the temperature. And then the relative humidity. Actually, this isn't relative. This is the humidity ratio, pounds of moisture per pound of dry air. And the relative humidity are these like sweeping lines. So that means relative to saturated air, which is at the top. So that curve is for saturated air. Like what fraction of total 100% saturation do you have? That goes like 80, 60, 40, 20. Right. So you have, and then if you have constant enthalpy in this, it says enthalpy, that goes in as a sideways line here. So once you evaporate the water, say if you have a wet bulb, let's see. There's a video on how this works. It's better than me, but basically if you have a wet bulb temperature, so the dew point is going to be like here. If you have a certain amount of water in the air, the dew point is like on that line. All right, so if your temperature matches the dew point, then rain forms, right? And then if you have a certain relative humidity, if you follow the constant isotherm up here, you get the wet bulb temperature. So the wet bulb would be like following the isoenthalpic adiabatic, the adiabatic line, constant enthalpy up to that point. That would give you the wet bulb temperature. Then the dew point is like if you go over here for some percent water in the thing. So you have like the temperature, the wet bulb temperature, and the dew point. So wet bulb temperature, you measure, so you have a thermometer, you have a kind of a rag on it that's soaked in water. It's got sometimes you see a thermometer has like a hoop at the top. I don't know if you've seen that. So you put the hoop on a stick and you wing it around until it reaches a certain constant temperature. That's a wet bulb temperature. So it's when it's totally evaporated the water. So the drier the air, the lower the wet bulb temperature relative to the dry bulb temperature, which is just the thermometers on the table. Right. So if you can get like the wet bulb temperature, and your dry bulb temperature, and the wet bulb's going to go along the isoenthalpic or the adiabatic line to your dry bulb, then that gives you these lines would give you the relative humidity of the air. And then if you go over here, that gives you the percent water, weight of water in the air versus the weight of the air in the air. Right, and then you could get the dew point from that too if you just slide over to this curve to the right on a horizontal line from that point. So that point is like where you are on your conditions. So you can see like if the drier your air is, you're going to have a lower relative humidity. And then if you're going to evaporate, so you're going to go isothalpic, then you have a bigger chance to drop the temperature. Like say you're really dry, say you're super dry, 10% humidity, and you're at 110 degrees, right? And then you go isothalpically all the way down to like 70 degrees. That's how a swamp cooler works. Like you're going to go through that process. There's a video that tells you that better. It's actually linked in the homework. It goes through exactly how this thing works. So anyway, so that's how these swamp coolers work. So this is evaporating water. You're just going isothalpic or adiabatic. Keep saying iso, adiabatic, and you go constant enthalpy. Zip up to here. That would be the wet bulb temperature, like what you could get by spinning the thing with the water on it. And then so you're better off being in dry air and at high temperature to get a big gain from this thing. Right? In other words, that swamp cooler is cooling you from 120 down to 70. That's a 50-degree drop just by blowing a fan over a sponge. Right? If you live in Cincinnati and it's like 100% humidity and it's like 80, then you have not as much to gain. Like you're only going to cool it by 5 degrees. That means that these things are only going to work like in certain regions. There's a map, like it works like out here. Swamp coolers work in that purple part, somewhat in the yellow part. Right, so a little bit of West Texas and then all of the mountain states and nothing around us. Right? You can't use it here. And then in the world, I think the green is where it will work. So there's a substantial amount of Africa, like the Sahara Desert, and like what's the name of that desert in Botswana? Kalahari. The Kalahari Desert's down here. And whatever desert, Saudi Arabia, Australia's all a desert. Right? So in Ethiopia, which is like right here, there's certain parts where it can work, like some parts it can't. So anyway, so that's kind of the swamp cooler thing. So the trick here is not be in a humid environment and be at a high temperature, right? Then you can get that to work. But there's ways to kind of get around that. This looks just like what the greenhouse guy had, right? That kind of ribbed thing might be the same thing. Anyway, the way to get around that is to start playing around with this psychometric chart, right? So you can do things like, so you have a stream that's going to cool the air down. So you just cool the air down, and then you've increased or you've changed the relative humidity. Then you do an evaporative step, or you can do the reverse of that, right? So basically, if you can dry the air out, then you can cool it down. So you can think you can make a machine to do this. That's the idea. Like you're sitting over here in Cincinnati, you want to cool it down to like from 90 to 70. And you don't have the room to evaporate to do that. You can only do like 5 degrees evaporating. So basically you can figure out a way to set up a machine that will do that for you without living in Albuquerque. Right. So that kind of machine has been made. People make that and it uses like solar heat to like dehumidify the air and then puts it through a humidification process to cool it down. So you end up with like perfect air coming out of it. It's possible to do it with using just the solar heat collectors, then some kind of engineered system to go through the psychometric chart in the right direction. This is a company in Australia that's making these things, but these kind of things could work here anyway, they can be engineered to work here. It's kind of complicated psychometric machine or something. But then there's like industrial evaporative coolers too that people So there's like an industrial scale side to this whole thing. But most of these, all right, so there's some that just use the same process like that, but there's some that use like ammonia to cool, which are also called evaporative coolers. So there's two kinds of evaporative coolers, I guess. They both are based on evaporation to cool. But one is based on evaporation of water, the other is going to be based on evaporation of chemicals. I guess that's the difference. So like large scale frozen fish and frozen vegetable plants use gigantic ammonia-based evaporative coolers. Because when you evaporate ammonia, it takes a lot of enthalpy out. You can put it through a process. Ammonia will absorb into water or can absorb into other things. You can condense it. You can chemically condense it. And then you can use the heat to drive the evaporation. And the evaporation of ammonia is like at -10 or -20 C. Right, so that you can get like a significant cooling. If you change the pressure on the ammonia, you can get it even colder. Right, so it's a process with no condenser. And then you use heat in that process to remove the ammonia from the absorbent material. So you use an absorbent so it's in a liquid state. It evaporates, that cools. It evaporates and goes into an absorbent, like you can use activated carbon, or you could use like lithium salts. You can use solutions to absorb it. And then you use heat to desorb it. So the heat is actually the compressor in the system, and the heat can just be solar heat. So you can use heat to desorb, and then it becomes a vapor again, and then condenses into the liquid, and then you put it through the same cycle. So it's a heat-driven refrigerator that can be run on sunlight. The problem is you need the pressure just exactly right in the system, and there can be no leaks in it. So you have like pure ammonia. It's 100% ammonia. It isn't like the stuff to wash your tables 2% in water. Ammonia loves to go into water, right? So basically the stuff you wash with is 2% ammonia. You already know like that'll knock you out the vapors from it. This is naturally a gas, right? And so anyway, so if you get 100% ammonia, it's going to kill everything. In fact, there was, when I did the thermal class, we did this safety thing that happened. And when they were doing the cleanups from the Gulf oil spill, I don't know when that was, a long time ago. And they had a frozen fish plant that had shut down for Christmas, right? And had this ammonia refrigerator. Then they do startup, right? Well, startup's like when the nightmare is going to happen because all that ammonia has been sitting there and suddenly the pressure goes through the roof. So that happened, and then it blew everything out. A huge cloud of pure ammonia gas went across the bayou to where the guys were fixing up the nets to go get the oil out of this, whatever BP did down there. You know, I mean, literally, I think like 100 people died. Like it was just a frozen fish factory. That's it, you know, some crazy ammonia refrigerator in a frozen fish factory. There's also a movie about these ammonia refrigerators about, I forget the name of it, but a guy goes to Central America or something and then tries to make ice there with ammonia refrigerator. I should find out what the name of that movie is. There's a book written and then also a movie in the 60s or something, I think. It's an old movie, you know. But anyway, ammonia refrigerators have been kind of popular items. Anyway, so oh yeah, that's the Nevada thing. I did have a picture of that. So yeah, I'll just pick up on ammonia refrigerators next time and go through. There's a few slides on that. So let me quit there. That's for today.